Hi everybody, in this video I will be giving you my take on section 6.5, which is about the average value of a function. Now I don't have a ton to say about this topic because I think the book covers it pretty well, but there are some things that I really like are in the book that I thought I would just reemphasize. So first off, we know how to take the average of a bunch of numbers. We know that to take the average of n numbers, you add them up and divide by n. And if we want to extend that to taking the average value of a function, we can kind of imagine what if it was like a real world function. Like what if we were trying to find, I don't know, the average temperature in the state of New York or something like that. Well, it would make sense to take 1,000 people and send them to different parts of New York, and then they all measure the temperature at some moment in time. And then we could use that to approximate the average. So for any old function, we can simply take a bunch of sample points. We're just going to call our sample points here x1 star through xn star. And then we can do f of those values, and then we can average those to get what we think the approximation of the average ought to be. However, we can do better. We want our sample points to kind of represent the interval over which we're trying to average. So we can therefore spread them out nicely. So if we spread them out equally, for example, by dividing AB into n equal subintervals, each with which delta x, and then choose xi star to be in the I subinterval, then we have a lot more confidence that when we average up f of the sample points, that we'll have a better approximation of the true average. Now, we've got this good idea of approximating the average, and it's not too hard to imagine that if we take the limit as n goes to infinity, we'll have the right idea of the average of a function. And we can define the average of the function on the interval AB to be this limit. But the only problem is, unless there's a delta x involved, we don't really have a Riemann sum, and we won't be able to convert it into a definite integral. So in order to force delta x to appear, we can take this equation right here and solve it for n. If you solve it for n, you're going to get n is equal to b minus a over delta x. So that allows us to replace the n in the denominator here with b minus a over delta x, which then, by the rules of fractions, becomes 1 over b minus a times this sum times the delta x, which now is the Riemann sum, 1 over b minus a times the sum from I equals 1 to n of f of xi star delta x. We can take the limit as n goes to infinity of that, and we will get exactly the integral. We will get exactly that the average value of the function can sensibly be defined as 1 over b minus a times the integral from a to b of f of x dx. Now, of all the formulas you learn about in Calc 2, this one is generally the easiest one to use because you're usually given the function and it's usually pretty simple to figure out what a and b are, and you just go ahead and do it. However, we do get an interesting geometric interpretation of average now that we're using calculus to find it, which I think is really neat because before, when you averaged up a bunch of numbers, there was absolutely no geometry involved at all. So we've defined the average value of a function to be 1 over b minus a times the integral from a to b of f of x dx. However, this integral is the area under the curve. And now the mean value theorem for integrals says that there's going to exist some number c in AB such that f of c is the average, which can be rewritten as they're saying the integral from a to b of f of x dx is f of c times b minus a. So this is the area under the curve. This part here can be interpreted as the area of a rectangle. It's a rectangle of height f of c and of width b minus a. And if we superimpose these on the same graph, we get this lovely interpretation of the average. The average value of a function is the value such that if you make that be the height of a rectangle over the same interval, then the area under the graph is the area of your rectangle. So it's a really neat way of introducing geometry to try and understand this new definition of average.